Welcome to CODECO's Project Second Pilot Demonstration. The Mobility Use Case. This pilot uses the CODECO framework to deploy an edge-based vehicular digital twin for safe urban mobility. Before running into the demonstration, let's clarify some concepts. A vehicular digital twin is a digital copy of the real world that tracks all the dynamic actors, in the case of the demo, vehicles, and uses this copy to simulate and anticipate future scenarios. Those anticipations can work to recommend or enforce actions in the real world so that dangerous situations are prevented and optimal behavior is ensured. To ensure operational safety, a vehicular digital twin must track every road user with extreme precision. Without this, the system risks causing accidents rather than preventing them. However, precise tracking is a major challenge. The infrastructure requires low latency, reliable updates from a vast number of vehicles. To achieve this at scale, we need an edge cloud solution supported by the CODECO framework. Here is how that infrastructure looks. We rely on V2X technologies. This enables peer-to-peer communication using reserved frequency bands, without needing standard Wi-Fi access points. However, to connect this moving traffic to the infrastructure, we need special antennas known as roadside units, or RSUs. Our specific use case focuses on VRU protection, protecting vulnerable road users like pedestrians and cyclists. Unlike cars, pedestrians don't carry V2X radios. They connect via standard 5G. The challenge here is integrating these two different data streams, V2X from cars and 5G from people, into one reliable digital twin to predict and prevent accidents. To make this work, we face four main challenges. First, communication, we need low latency. Second, interoperability, different actors must be able to speak to each other. Third, monitoring, we need real-time visibility. And finally, scalability, as the number of cars increases, the system must adapt instantly. This brings us to the edge cloud continuum. Instead of sending all data to a distant cloud, we process data closer to the street level, using edge nodes to maintain that critical speed and reliability. Let's look at the speed requirement. For direct vehicle-to-vehicle communication, the industry standard for end-to-end latency is under 25 milliseconds. Currently, direct V2V can achieve under 2 milliseconds. This is the benchmark we are aiming to preserve. But when we introduce the network, sending a message from a vehicle to the server and back to another vehicle, latency increases. This is V2N2V. Our goal with CODECO is to reduce this end-to-end latency by over 80% compared to standard cloud approaches. This diagram shows the complexity of the protocol stack. We are reshaping the standard OSI model. We aren't just using standard TCP/IP, we are integrating complex ETSI standards like geonetworking and BTP to handle safety-critical messages. To achieve interoperability, we use a centralized component that aggregates everything into a dynamic map. Cars send CAM messages, cooperative awareness messages. Pedestrians send VAM messages, vulnerable road user awareness messages. The system translates both into a single view. Here is a glimpse of our monitoring stack. We utilize tools like Prometheus, Grafana, and Loki. This dashboard allows us to track metrics like CPU usage and temperature across the different nodes in real time. For scalability, we rely on the CODECO framework, which is based on Kubernetes. Because our system is cloud-native and stateless, CODECO can intelligently migrate workloads between different edge nodes to maintain optimal performance as traffic moves. This slide illustrates our architectural transformation. We moved from a coupled architecture, where components were stuck together, to a decoupled architecture. By separating the application layers from the network layers, we gain the flexibility to move specific services to where they are needed most. Here is the detailed view. On the left, we have the edge cloud continuum managing the logic. On the right, we have the roadside units communicating via CV2X, and smartphones communicating via 5G. They all feed into the dynamic map. How does the system decide where to run the processing? The PDLC, Privacy Preservation Decentralized Learning and Context Awareness component, scrapes metrics like latency. It then tells the pod placement operator to migrate workloads from Edge 1 to Edge N seamlessly. In a real deployment, this looks like a distributed system. We have multiple edge nodes handling the heavy lifting of basic services, while the central cloud handles the aggregated visualization for the road operator. Measuring success in a digital twin is complex. We have to consider errors in tracking. If the digital world lags behind the real world, the twin is no longer accurate. We need metrics that capture this drift. To measure this, we use Age of Information, or AOI. This metric integrates both latency and reliability. Simply put, it measures how fresh the data is. The lower the AOI, the better the system performs. We also use Penalty Age of Information, or PAOI, which translates that time delay into distance error. If the system is slow, the digital car is in a different location than the real car. This metric captures that danger. We've explained the pilot. Now, we will explain the demonstration peculiarities. For our demo, we chose a highway scenario rather than a city center. Why? Because urban mobility is erratic. In a highway scenario, vehicles flow continuously, making it easier to benchmark scalability and reliability effectively. In this highway scenario, we model distinct coverage areas. Each roadside unit has a limited range. The simulation is precise, it considers the physical coverage of each RSU, meaning that each unit only receives data from the specific vehicles currently passing through its zone. This creates a realistic, segmented flow of information. Moving to the topology, our simulation connects each RSU directly to a single edge node. This simulates the behavior of an edge server physically located close to the vehicles it serves. This setup is crucial because it allows us to observe the real-world effects of a distributed network, specifically, how having multiple edges impacts the latency for different connected users. In the demo setup, we have simulated cars and RSUs feeding data into the CODECO framework. The PDLC monitors the system and triggers migrations when necessary. The physical hardware consists of Intel NUCs representing the cloud, and Raspberry Pis acting as edge nodes. An NVIDIA Jetson Orin runs the heavy traffic simulation. And finally, the results. This graph shows the age of information over 5 minutes. Notice the drop. When the system becomes unstable, PDLC reinforcement learning model kicks in, optimizing the workload placement. You can see the AOI drop significantly, stabilizing the solution. Looking at a 12-hour period, the pattern holds true. Whenever the system detects instability, shown in the green spikes, the optimization executes, bringing the age of information back down to a safe, low level. This proves the CODECO framework successfully ensures safe urban mobility. Now, let's transition to the live demonstration. This demo simulates traffic on the C16 highway. This is a major route near Barcelona, chosen specifically because it typically experiences high traffic density, providing a realistic test environment. Let's orient you to the screen layout. In the browser window at the top left, you can see the track nodes moving along the highway. In the bottom right corner, you see the terminal window which is controlling the active demo components. And on the left side, we have the Grafana dashboard. This monitors the performance of the edge cloud deployment in real time, visualizing the specific metrics we described earlier in the presentation. As you watch the vehicles, notice the blue circle drawn around them. This is the circle of uncertainty. It represents the positional error, or the difference between the digital twin and the real world, caused by momentary bottlenecks in the edge cloud deployment. Furthermore, every service involved in this deployment is being closely monitored. The dashboard isolates the delay that each individual service adds to the overall digital twin. This granular visibility proves that the system can detect, and even prevent, bottlenecks that would otherwise lead to a system malfunction. Here, we can observe a rescheduling event. Notice how a service migrates to a different node. The system identified a performance dip and automatically moved the service to improve execution. This demonstrates CODECO's ability to detect bottlenecks and act upon them autonomously. This concludes the demonstration of the second pilot of the CODECO project. For further information, please visit our webpage or follow us on LinkedIn. Additionally, the source code for this demonstration is fully open and available in the Eclipse CODECO GitLab repository. Thank you for watching.